This slide set is about classless interdomain routing. The starting point here is an IP address such as 193.175.1.1. If you have just this IP address, does it imply already the network mask, or in other words, is it clear how many bits of the address belong to the network part and how many bits to the host part? The answer nowadays is no. However, until 1993, a class-based address schema has been used, where the first bits indicated how many further bits belong to the network part. You can see the different classes in the table. You can also see that the classes were quite different. In a Class B network, you can distinguish more than 65,000 addresses, but in a Class C network, there are just 254 addresses to distinguish between hosts. The 8 bits that are available provide 256 different values, but you can not use 0 and 255 because they refer to the network itself and serve as broadcast address respectively. As I mentioned before, this schema is no longer valid, but still often you hear people talking about Class C or Class B networks. Therefore, I'm still showing you the schema here. On the previous slide, it is already mentioned that this schema leads to a wasteful use of IPv4 addresses, which became an issue over the years. Here we see an example of a company that needs 2000 IP addresses. Since a Class C network is not sufficient, the company receives a Class B network. However, this implies that more than 63,000 IPv4 addresses remain unused because the company does not need them. The solution is the classless interdomain routing, which is more flexible. The abbreviation for it is CIDR, which is just spoken as CIDR by networking people. The network part can end at any bit so that address spaces of suitable size can be formed. A new notation has been introduced where the number behind the slash indicates how many bits belong to the network part. In our example, we can determine that 11 bits for the host part are sufficient for the company because 11 bits provide 2048 values, which is more than needed for the 2000 hosts. In addition, we can see the notation for an example network. On the next slide, we see an example how subnetworks can be formed when CIDR is in place. There is an internet service provider which administrates an address space 200.23.16.0/20. So in this address space, 20 bits are given and further 12 bits are available to distinguish between hosts. In the network mask, the first 20 bits are ones and the remaining 12 bits are 0. In the decimal notation, the network mask is 255, 255, 240, 0. However, in this example, the ISP does not want to distinguish its own computers but wants to provide address spaces to its customers. There are 4 customer organizations which demand networks of equal size. To form these customer networks, it is necessary that they get unique network prefixes. The idea of these network prefixes is that you take 2 additional bits which can be used as 00, 01, 10, and 11. As a result, there are /22 address spaces for the customers, such as 200.23.16.0/22 for the first customer network. In these networks, 10 bits are available to distinguish between the hosts. The network masks for the networks are 255.255.252.0. In the following, I'm showing you, based on another example, that this way of distributing the IP addresses is reasonable to keep routing tables small. In this example, there's an ISP-A which has 8 customers. The ISP has provided /23 networks to the customers, but towards the internet it can aggregate these address spaces and can just announce a /20 address space. So the routers in the internet have just one entry in their routing tables instead of 8 entries. On the slide you see another ISP called ISP-B. Now the question is, what happens if a customer organization leaves ISP-A and becomes a customer of ISP-B? The customer organization wants to keep its address space because it does not want to do reconfigurations. We see on the following slide that the customer organization can keep its address space and that ISP-B announces this specific address space in addition. ISP-A does not change its announcement so that it is not replaced by 7 new entries in the internet routers. This implies that, for example, the IP address 200.23.18.3 is both part of 200.23.16.0/20 and 200.23.18.0/23. The routers in the internet apply the so-called longest prefix matching rule. In our scenario, we have prefix lengths of 23 and 20, so that 23 is longer and therefore this more specific entry is being used. In this way, the IP packets for this address are provided to ISP-B.